So I'm going to start with some review of some basic concepts from probability and statistics. I think many of you took Intro to Stat last year or last semester or at some point in the past, but for some of you, it might be distant. And then after that, we'll do simple linear regressions, just one predictor or covariate. So first, the probability and statistics review. The first concept to know is the sample space. We're going to get to what is a probability distribution, but before we can define that, we'll just have to define what a sample space is. And that's the set of all possible values that a random variable might take. For example, if the random variable is the outcome of the roll of a die, then the sample space is 1, 2, 3, 4, 5, 6. If it's the flip of a single coin, it's heads or tails. If it's the outcomes of 2 flips of a coin, it's heads, and tails, tails. And let's say it's a survival time, then it could be any number greater than 0, like any continuous number. Events are subsets of the sample space. So for example, in the 2 flips of a coin sample space, an event could be that both coin flips are the same. So that would be heads, heads, or tails, tails. So it's a subset. And in the survival example, it could be survival greater than 1 year. So that's also a subset of all numbers greater than 0. So now probabilities are numbers that get assigned to these events such that probabilities are between 0 and 1. The probability of the whole sample space is 1. It has to be, because that's the set of all possible outcomes. So it has to be something in there. And for any 2 disjoint events, so for example, both coin flips are the same as one event and the coin flips are different, would be another disjoint event. There are no outcomes that are in both. So for any 2 disjoint events, the probability that one or another occurs is the sum of their individual probabilities. So that's it. That's all that's required for something to be a probability distribution, that it assigns probabilities to events and that these properties hold. Of course, you want it to be useful. You want it to have the interpretation that these probabilities correspond to how likely the events are as well, but that's not required. So here's an example of a discrete probability distribution. So a probability distribution, it's like a key that allows you to figure out what the probability of any possible event might be. And for the example of rolling 2 die, there are 36 possible outcomes. So here's the sample space on the bottom, 2 through 12. Those are the possible outcomes. You could just list every single outcome in there and its probability, and then that allows you to then compute the probability of any event. So here, there's only one way you could get the sum being 2, and only one way you could get it to be 12. There are 6 ways out of 36 that it could be 7, so that's the most likely. And then if you want to say what's the probability that it's odd, you can just take the sum of 3, 5, 7, 9, 11, right? You could get the probability of any event just from listing out the probabilities of each outcome when it's discrete. When it's continuous, then a common way to get a key to allow you to find out the probability of any event is to define a probability density function. So here's an example with 10,000 observations of heights of 7-foot doors in inches. 7 feet is 84 inches. 7 feet is apparently a standard height for a door, but the doors are often not perfect, right? There's some error in how they're constructed. So here's the distribution of the actual heights of 10,000 7-foot doors, each dot being a door. And each column, you see the number of doors that were in that range, right? In the range defined by this segment of the x-axis. So a density is something such that if you take the integral of the density over a span of values that the variable might take, you get the probability that the value is in that interval. So here, for this range where there were 730 doors, if you do a histogram, you can approximate the density by saying that, so the probability that you're in that range is 730 over 10,000. The width of the interval is 0.025. It's 83.935 minus 83.91. If you divide the probability by the width of the interval, you get the density. So then if you multiply the density by the width, you get the probability back. This isn't something that we ever have to do. It's just intuition about how you get a density and how densities tell you the probability that variables are in intervals when you have the continuous. So yeah, we're never going to actually break it up discretely like that in a normal distribution. I just wanted to build the intuition here that you integrate densities over ranges to get the probability that the value is in that range. But we're not going to actually do integrals in this class, right? Just think of integral as like the area under the curve, and R will do it for you anytime that we need to compute a probability from a continuous distribution. So here's an example for a normal distribution. If a random variable follows a normal distribution or any distribution, then the probability that its value is in a given interval, let's say between A and B, is the area under the probability density function. That's what this is a graph of in that interval. So it's the area under this density function between A and B. So it would be P norm of A is the probability, is the area under the curve to the left of A. And same with less than B, you get that by P norm of B with the mean and the standard deviation of this normal distribution. If you want to know the probability that it's between A and B, you can get the probability that it's less than B, which is this whole area, minus the probability that it's less than A, just leaving you with what's between A and B. And then if you want to get the probability that it's greater, you can just do 1 minus P norm. Okay, another equivalent way to give you all the information that you need to know to be able to determine the probability that a random variable is in any interval you care about is the cumulative distribution function. So on the top here is the density function for a normal that we were just seeing. And on the bottom is the cumulative distribution function. So the CDF is the probability that is P norm, and R P norm gives you the CDF. It's the probability that the random variable is less than any given number. So for A, it would be just the area under the density curve is this value here in the CDF. Those are just both ways to like represent probability distributions, right? So a distribution, again, is if you have a random variable that you care about, the distribution is what generates it. And it's like a key to being able to find out the probability that random variable will take any value that you care about. A parametric model indexes or defines distributions within some class by parameters. So for the normal distribution, you could index specific examples of normal distributions by their means and their standard deviations. So this is the normal density function. It's messy. We never have to actually use it in this class. Just here it is. And you can see that it depends on the mean and the variance or standard deviation. And here are 4 examples of normal distributions that look different depending on how you change their mean, which is their center, or standard deviation, which is like their spread, right? And so often the goal of statistical inference is you assume a parametric model. So you assume that your data were generated by some distribution from a class that you can index by parameters. So assume it comes from a normal distribution, for example, with parameters mu and sigma, and you want to try to find the values of the parameters that define the distribution that best match your data. And you want to find the range of parameters often that are compatible with your data, because you're not certain about, just from looking at data, what the exact distribution is that generated it. Just to repeat again, there are parameters that define the distributions in that class. So like for any values of those parameters, you get a different distribution, like these normals here. And given your data, you want to find the values of those parameters that are the closest fit to your data. And you also want to get the range of parameter values that are at least compatible, at least might have generated your data. Here's a histogram for the doors. This is very close to like a normal distribution, right? It's very unlikely that these data would be generated by a normal distribution with a mean that's far from 84. And whatever the standard deviation of this is, it's unlikely that the standard deviation of the true distribution that generated it is far from that. So that's just the basic idea of statistical inference. Okay, so now let's apply this to simple linear regression. So simple linear regression is a particular parametric model where instead of just assuming that a variable comes from a normal distribution, we have two variables. You have an outcome variable y and a predictor or covariate variable x. And you have a regression function that you're interested in. It's just the conditional expectation of y given x. It's what the average value of y is if you observe that x equals x. And you assume that y is generated by a normal distribution centered at its expected value given x, right? And you assume that expected value is a linear function of x. And the parameters for this model then are the coefficients of that linear function of x. So it's beta 0 and beta 1. So here, this picture, I think, nicely illustrates what the model is for the data generating process of a linear regression. So you assume that there's some line, right? A linear function of x where beta 0 is the intercept. That's the value of the line when x is 0. And beta 1 is the slope of the line. And that the outcome y, each dot would be an observation that you might see of x and y. The outcome y comes from like a normal distribution centered at the point on the line corresponding to x. So like here for x equals 2.5, you would go up to the line and then you'd take a normal, you'd draw a normal variable centered at that point on the line corresponding to 2.5. Same for negative 7.5, you'd go to that point on the line. And then there's a normal distribution with standard deviation sigma, give you your y value. So it's like y is a linear function of x plus noise, and the noise follows a normal distribution with mean 0 and standard deviation sigma. The parameters that define this distribution are beta 0, beta 1, and sigma. The goal of regression is to find the values of these parameters, assuming that your model is correct, that really your data were generated in something close to this way. You want to find the parameters that best fit your data. And then you also want to get the range of parameter values that are at least compatible with your data, assuming that this model is true. So we'll go through some examples of this. First, just a repeat from last class. An example we gave was forecasting the election from the economy, where you have one predictor variable, and it's the average recent growth in personal income. And you have the outcome variable is the incumbent party's vote share. And here's the actual observed data. It really does look like it's close to a line, like maybe it really was almost generated in, according to the model we just described. And if you find the line that best fits this data, it's y equals 46.3 plus 3.0 times x, right? That's this line best fits these points. These are the parameters, 46.3 and 3.0, that define the line that gives you the best fit to the data, which are the points. Here's another example, a more public healthy example. This is a data set where each point is a county in the United States. And on the x-axis is the percentage of people in that county who are below the poverty line. And on the y-axis is the cancer death rate per 100,000 population in the county. So here's a scatter plot. You can see that there's a vaguely linear relationship here, right? As poverty goes up, so does cancer death rate. Here's the code that produced this plot. So you might want to fit a linear regression model to explore the association between poverty level and cancer death rate. The way to do it in R is to run these two lines of code. You'd say the model that you want to define is a linear model, LM, with the outcome variable cancer death rate and predictor variable poverty using the data set that was called data. And then here's the summary of the model. And then this is what R will spit out. So coefficients, if you look at the column estimate, this is your regression function. This is the beta 0 and beta 1, the parameters that define the linear function of x that gives you the expected value of y under your model. So the estimate is that the number of deaths per 100,000 in a county. The expected number of deaths is equal to the poverty, is equal to 147.3 plus 1.86 times the percent poverty in the county. Right, so this is your best guess. And here in red, that's the line that was fit by the model added to the scatter plot. Okay, back to the output. There's a lot more. This gives you the standard error for each of the regression coefficients. So the standard error you can think of as the thing that you need to add and subtract 2 times it to get the confidence interval for each coefficient. You might care in particular about the relationship, the slope of the line, the relationship between poverty and cancer death. So again, the interpretation here is that if one county has a 1% higher poverty rate, then the expected cancer death rate per 100,000 is 1.86 higher in that county. Now, you might want to know the range of coefficient values that are actually consistent or compatible with the data, right? So the confidence interval would be 1.86 plus or minus 2 times the standard error. So 0.07 is quite small. And 2 times 0.07 is 0.14, is pretty small compared to 1.86, right? So it would be like 1.72 to 2 would be the confidence interval. And that's pretty precise, right? But the kind of qualitative interpretation of this association wouldn't differ very much across values in that confidence interval. And then this right-hand column gives you the p-values for the coefficients. So these are highly statistically significant, less than e to the negative 16th power. So basically 0. It's saying that, if your linear model is correct, if the real coefficient value is 0, then the chance that you might estimate it to be greater than 1.86 is essentially 0. So you're not going to observe this slantiness of the scatter plot just by chance if in reality there's no association between poverty percentage and cancer death. And then finally, we have the residual standard error, and we have something called R squared. So the residual standard error is your estimate of sigma here. So residuals are the difference between the actual observed values of y, the y values on these points, and the red line. So the predicted values for y, which we often denote by y hat, the difference between the actual and predicted values, or actual and conditional expected values under your model, are called residuals. And so the residual standard error is your estimate for sigma in your model. That's one of the parameters, right? It's like how much noise do you add to the line to get the actual observed value under a simple linear model. You might often want to know like how much of the variance of the outcome can you explain with your predictors. So in the poverty and cancer case, on the left-hand side, we have a histogram of cancer death rate minus mean cancer death rate. This just shows like the spread of cancer death rate across counties, like how far it varies from its mean. And then on the right, you have a histogram of observed cancer death rate minus predicted under the linear model. So it's like the spread away from the red line versus just the overall spread from top to bottom, ignoring the predictions, right? If sigma is very small, or if the predictor variable explains a big chunk of the variance of the outcome variable, then R squared will be really high, because this variance, the variance of the residuals, will be really small. Everything will be close to the line, right? Compared to the variance of the outcome overall. So this ratio will be close to 0. And so R squared will be close to 1. So if you like perfectly explain the outcome with your predictor, so all the residuals are 0, then R squared is 1. And if you explain a lower proportion of the variance, so there's still a lot of noise here, these two histograms look pretty similar to each other, right? Then the R squared will be closer to 0. So here, for example, it's 0.18. So there are a lot of factors other than poverty that are influencing variation in cancer death rate across counties. This is a histogram of the residuals. So this is the y minus y hat. So for each value of y, we subtract the red line corresponding to its x value and take the histogram of all of those. Here we have just y minus the overall population mean of y. So ignoring x. This is just like gives you a sense of the spread of the outcome overall. This gives you a sense of the spread of the outcome around its predicted value given x. So again, looking at this model here, that histogram I gave was like approximating this normal distribution, whereas the other one would be approximating the overall distribution of y, right? It would be a big normal. Here's another example. An RCT looking at whether this drug Sulindac prevents polyps. This was an RCT of just 22 patients. It was done in like 1993. It was published in the New England Journal of Medicine. Here's the data. Treatment equals 0 is no Sulindac. Treatment equals 1 is Sulindac. And the outcome is number of polyps 12 months after baseline in the RCT. You can fit a linear regression to data where the predictor variable is categorical, or in this case, binary. Between 2 points, there's a line. And a linear regression is a simple way to frame a comparison between two groups, actually. So we could, again, run a linear model where we say the outcome is number of polyps at 12 months. The predictor is treatment, which is 0 or 1. And the output is of the same form as our previous linear regression. And we look at the coefficients. And what we're interested in would be the treatment effect, right? What I have in the slides, which I'll fix, is treatment was originally coded as 1 or 2. That's why this says 61.38. It should be 0 or 1. Here, let me just actually show you the real thing. Here's the summary where treatment is 0 or 1 and not 1 or 2, so it's more interpretable. So the intercept is the expected number of polyps after 12 months when treatment is 0, so that's 35. And the coefficient for treatment equals 1 is the treatment effect. So that's the slope of the line, right? The slope of the line is the difference between what it would be with treatment equals 0 and treatment equals 1. So that's what's of interest in an RCT. And so a kind of standard easy way to analyze an RCT is to just fit a linear regression. And you can get the standard error for the effect as well. So here it's 7.4. So that means that you add or subtract 14 to the effect estimate of -25 to get the confidence interval. And that comfortably excludes 0. So there's high confidence from this RCT that there is the preventive effect of Sulindac on polyps. And this is the same p-value. So it's 0.028, which is very low, so highly statistically significant. And this is the same exact thing that you would get from a t-test for comparison of means, which is maybe the standard approach that you guys have been taught in the past for analyzing this type of data, where you have two independent groups. You can also just use linear regression for that. Let me just show you again, in the more interpretable coding. So, right, so when it's 0 and 1 and the intercept really does correspond to the expected value of the outcome under no treatment, then it's saying that in expectation, without treatment, people would have 35 polyps after 12 months, but plus or minus 10, right? 2 times the standard error of 5. You usually wouldn't be interested in a p-value for the expected value of the outcome under no treatment. Like they give it to you anyway, but you're not really interested in the null hypothesis that there would be 0 polyps in the absence of treatment.